So in the previous lecture, we have seen how to write from scratch, how to use great orthogonality theorem and use it to write from scratch the irreducible representation, all the irreducible representation that constitute the character table of a given point group, right? So we have taken example of C2V and C3V point groups, and we worked out using that, and I expect that you do it as a home assignment to pick up few point groups and do it yourself, all the calculations, to see if you are able to write the character tables given any particular point group. Okay, so now in this lecture what we will see is how do we go from reducible representation to irreducible representation. Okay, so reducible representation has its own importance and irreducible representation has its own importance. All the properties which lie along the unit vectors which form a basis for irreducible representation are defined by irreducible representations, right? And then we still have to use certain basis sets to actually identify. We will see that later when we discuss the applications, that we have to write down reducible representations and then we have to actually reduce it to IR representation. So let's see what is the basic idea. So the idea is, let's say if we choose any basis set and matrix under any given symmetry operation R for any given point group, for let's say this is the character table we are writing, and then we have any given point group G, and let's say this is tau 1. So under any given symmetric operation we have certain matrix, right? The order of the matrix will depend on the basis set chosen. So this can be a diagonalized matrix or non-diagonalized matrix. So this will have matrix elements such as, so let's just call it A1, A2, A3, A4 and so on, right? So I'm not giving you the final dimension, so it can be any dimension, right? So now we have to diagonalize it to be able to reduce it, right? And how do we diagonalize it? Sometimes you will get diagonalized matrix by itself, but many times you have to actually diagonalize it. How do you diagonalize it? Let's call this matrix as A. So to go from A to A prime, you have to find a matrix U that we have seen earlier, that you can do it, right? And you go to A prime, where A prime is a diagonalized matrix. What do you mean by diagonalized matrix? That you will have matrix elements only along A, let's say 5, A 11, something, okay, and rest everything here and here will be 0, right? So these are called as diagonalized matrices, which you can obtain by doing a similarity transformation on A. But for that you have to, the important point is, how do you find A? This is not a trivial thing. How do you find U, right? How do you find U and U inverse, which is not trivial, which will give you a diagonalized matrix? So how do you do that? How do you find this out? The important point here is that trace of A is equal to trace of A prime, right? That we have seen. Similarity transformation does not change the trace of the matrix, right? And we also know that because this is a diagonalized matrix, so all the individual matrix elements will actually come from the irreducible representations, right? So the trace of A prime as individual matrix elements, right? A1 plus A5 plus A11, which are nothing but trace of A1 matrix. It can be 1 cross 1 or 2 cross 2 and so on, but it is a irreducible representation, or trace of A5 and so on, right? So this means that I can always say that the character or trace of a given irreducible representation under a symmetry operation is equal to, so this is nothing but trace of A prime. So this will be equal to linear combination of, let's call it as J, AJ, and this will be character jth representation under the symmetric representation, symmetry operation R, right? So now this is a linear combination. It can be a1 can, so for example, this number can appear twice here, same number can appear twice. So what I mean is that you have tau, let's say a reducible tau can be tau 1 plus 2 tau 2 plus 3 tau 4 plus 1 tau 3 and so on, right? So these are individual IR representations. So tau reducible is composed of several IR representations. So tau reducible is a linear combination with some coefficients, because we don't know how many times tau 1 will appear in tau reducible, how many times tau 2 will appear in tau reducible. So that is defined by this coefficient AJ, right? And then this is the character of jth irreducible representation under symmetry operation R. So this is very clear, so that any reducible representation can be broken down into a linear combination of irreducible representations. Now the problem is we don't know how to find A, right? AJ. So we don't know this. We know how to write it from scratch, how to write irreducible representation from scratch. So this we know. We know how to write a reducible representation given under any basis set. We know this. So we can find out the trace of any matrix under any reducible representation. So this is also okay, this is also okay, but we don't know how to find AJ. So let us see if we can actually do this maths, okay? And write down this again. So chi R is equal to summation over J, all J. AJ chi jth representation under R. Did I write J? Yeah. Okay. Alright, so now let's say if we multiply both sides by chi I R and sum over all R. Okay, so if we do this, what do we get on left hand side? We get chi R summation over all R, and what do we get on the right hand side? Summation J summation R AJ chi J R chi I R, right? Now let's see what do we have here. So we have this term, we have this term, and we have this. Okay, we can always take AJ out of this summation R, right? So I can say summation over J AJ summation over all R chi J R chi I R. Now this is a familiar figure from third property of GOT, which we have discussed already. This amounts to H delta Ij, right? Character under any given symmetry operation, product of two different characters for two different IR representations under a given symmetry operation, and summation over all symmetry operations would give you order of the group multiplied by delta Ij, right? So this is there. Now we have summation over J. Summation over J means that all the values of J we have to take, but the only value of J that will survive, which is equal to I. All other summations here will go to 0 because we have delta Ij term here, right? So this means that the only J value that is equal to I will survive, right? So now that summation is expanded, so I don't have to write the summation. So what we have to do is, now J becomes I, and what we are left with is H, right? Because for I equal to J, delta Ij is equal to 1. For all other J values, this goes to 0, right? So we are left with AIH, and here we have summation r chi r chi I r, right? Now this problem is very simplified. Here we wanted how do we get a, and we have got it. So 1 over h summation over all r, character under reducible representation, character under irreducible representation, right? So we know this, we know this, we know the order of the group, so we can calculate ai, right? Okay, now let's take an example to see whether we can do it or not. So let's take again C3V point group example. So now I'm assuming that you are able to write all the irreducible representations by yourself using the rules of GOT, right? So you have E 2C3 3 sigma V. Again, because I'm writing only the traces, so I'm combining the class elements here because class elements will be same. So we have tau 1 as 1 1 1, tau 2 as 1 1 minus 1. We have seen this earlier, and tau 3 is 2 minus 1 0. There are 3 irreducible representation because there are 3 classes, right? Now let's say I have chosen certain basis set where I get a reducible representation as, well, I don't know to start with whether it's a reducible or irreducible, so you can always test it as we tested for water example, whether this will be a reducible representation or irreducible representation, again using rules of group GOT, right? So that also I'm assuming that you know how to distinguish between whether it's a reducible or irreducible representation. Okay, so now once you have written the character table and you have written the reducible representation under certain basis set, let's say some basis set. So now as per this rule, so we should have A1 tau 1, A2 tau 2. This is what we defined earlier, right? A3 tau 3. Okay. So now our job is to determine what is A1, A2 and A3 so that we can break down this tau reducible into linear combination of the irreducible representations. Okay. So let's determine A1 first. So for A1, we have to write 1 over h. What is h here? H is 6, right? 6 elements. So h is 6. Now you have to take summation over all r, okay? And you have to multiply the trace under tau 1 to the corresponding value of this, right? To the corresponding value of tau, which is basically what I'm saying is aj is equal to 1 over h summation over all r, character under reducible representation and character under irreducible representation, right? This is what we are going to use. Alright. So what I'm going to do is I'm going to pick up 5 and multiply it with 1. So pick up 5, multiply it with 1, then pick up 2, multiply it with 1, and then pick up minus 1, multiply it with 1, and then summation, right? And I'm also going to tell you one more point here, that the class sizes also have to be multiplied here. So let's just see that class sizes have to be multiplied with this multiplication because each class element has same trace. So instead of repeating that, we'll just multiply it with 2. So we'll see that. Okay, so 5, which comes from here. Then you have 1, which comes from here, into class size, which is 1 over here, right? Okay, then 2 into 1 into class size. So this is very important that you multiply it with class size. Plus minus 1 into 1 into 3. Remember, we have to take summation over all symmetry operations, and if we do not multiply it with class size, that means we are not taking summation over all symmetry operations, because then we'll leave out C3 square, or we'll leave out sigma V2 and sigma V3. So we have to include all of this. So that's why this multiplication with class size is important, right? Now what do we get here? This is 5 plus 4 minus 3, right, divided by 6. So what do we have here? 1. So A1 is 1. That means contribution of tau 1 into this reducible representation is 1 times, right? So we can, okay, let's go ahead and do for A2. So let's do it here. So for A2, again, this will be 1 by 6. Then I'll just do this 5 plus 2 into 1 into 2, that is 4, minus 1 into minus 1 into 3, that is plus 3, right? This gives me A2 as 2, right? Then A3. And now to test whether your calculation is correct or not, these numbers have to be natural numbers or whole numbers. 0 can also come, right? Whole numbers. So because this cannot be in fraction, contribution of any given irreducible representation cannot be in fraction for a reducible representation. So again, so 5 into 2, 10, minus 4, and then 0. So what do we have here? 1. So that way I can say that tau reducible is equal to tau 1 plus 2 tau 2 plus tau 3, right? So this is a very, very important result, that now we are able to write any given reducible representation into linear combination of irreducible representations. We will see that how important this is when we'll get down to applications. Okay, so for home assignments today, so let's take this example and try to reduce this. Another tau reducible will be, which is 7, 1, and minus 3. So try to work it out. See if you can find out the linear combination of tau 1, tau 2, tau 3 here. Okay, so that is all for this lecture. So now we have learned how to write down a reducible representation. We already knew how to write down a reducible representation. We already knew that how to write a irreducible representation from scratch without worrying about what the basis elements are or what the basis sets are and what the effect of symmetry operations are and so on, entirely using GOT. And now we have seen how to convert a reducible representation into irreducible representations, linear combination of irreducible representations. So that ends the great orthogonality theorem discussion, and next class we'll be discussing the character table, how to, like, what are the different portions of character table, what is it constituted by, what are the important regions, where are the basis sets identified, and so on and so forth. Okay, so that will be done in next class. Thank you.